Here we go. This Zoom session is being brought to you by the fractal set of itself. All right. Today we're going to be doing 3 sections, although it's really more like 2.5, and thus end the chapter. With this section 1.5, it's an extra credit set on the homework. So I'm not going to go and review any of it. I'll just go over what the basics idea. So this will basically describe various constant functions and their graphs. So constant graph is a horizontal line at a height, whatever the constant is. Y equals x, called the identity function. It's a diagonal line through the graph. Y equals x squared is this U-shaped curve called a parabola. Y equals square root of x is basically a parabola on its side, but only the upper half. So these are related because they're what are called inverse functions, which we'll be seeing more of later. Here's a graph of y equals x cubed. Here's a graph of y equals cube root of x. Again, these two are related basically by flipping through the diagonal. I'll discuss that in a few minutes when we talk about inverse functions. Y equals 1 over x has a shape called a hyperbola. Y equals absolute value of x. Its graph is a V shape like this. Here we have what's called a piecewise defined function. I'm not a real fan of it because, as you can see, there's gaps in it. This function has different definitions for different parts of the line. For x equals 1, for this one, for x equals 1, y equals 1. So it's this horizontal line like this. Y equals x between -1 and 1 for x. So it's this diagonal line here. And y equals 2 for x equal less than -1. So it's this horizontal line like this. So it's basically 3 pieces of graphs glued together with duct tape. And as you can see right here, there's a gap. Here it's approaching -1. Here it's approaching 2. And there's this gap where it makes a sudden jump from one to another. Mathematicians don't like that. It's called a discontinuity. It makes things a little inelegant. Here it's continuous. These 2 lines join up. Okay, well, let that be for now. So, okay, this is 1.5. It's extra credit set in the homework. These are the basics of it. We proceed to 1.6. 1.6. Here we're going to shift around function graphs. We're given a graph of a function, and what happens is we take if the function f of x minus h, that plus k, it's the same as this graph, only shifted left, right, up, or down. For example, let's take y equals absolute value of x. It's this V-shaped curve. All right, well, curve, whatever. And if you add k outside, so y equals absolute value of x plus k, that shifts this graph up or down by k units. Here's y equals absolute value of x. Here's y equals absolute value of x plus 1, shifted up 1 unit. This is y equals absolute value of x plus 2, shifted up 2 units. Here's y equals absolute value of x minus 1, shifted down a unit. Is y equals absolute value of x minus 2, shifted down 2 units. So y equals f of x plus k. This shifts the graph up k units if k is positive, down if it's negative. Now, if instead of adding a k outside the absolute, we subtracted h inside the absolute value. Now this will shift the graph left to right. Here the idea here is if h is positive, it shifts it to the right because everything is h units delayed. So this is the graph of y equals absolute value of x. Y equals absolute value of x minus 1 is delayed by 1 unit, so it's shifted right 1. Here's y equals absolute value of x minus 2, shifted from here 2 units. Here's y equals absolute value of x plus 1 graph. Now this plus 1 advances it by a unit, so it's 1 unit shifted to the left. Y equals absolute value of x plus 2 shifts the graph 2 units to the left. In general, y equals f of x minus h. It shifts the graph right h units if h is positive, left if it's negative. Now if you put these two together, y equals f of x minus h plus k, for constants h and k, it will shift the graph right h units and up k units if h and k are positive. So if here's the graph of y equals f of x, then y equals f of x minus h, that plus k, looks like this. This shifted right h, up k. Now we talk about multiplying a function by a constant. Y equals a times f of x. What this does, it will stretch or squeeze or flip the graph vertically. If a is positive, it'll stretch it vertically. So for example, here there's wave y equals f of x. Y equals 2f of x is wobbles twice as tall and twice as down. So for a positive, it's a vertical stretch. If a is between 0 and 1, it's a vertical squeeze. For y equals a half x, this will take this wave and squash it, a lower amplitude. And if a is less than 0, then it flips up for down. So here this goes down, then up, then down, then up. Here, y equals minus f of x first goes up, then down, then down, then up. And down. So this graph flipped upside down is this graph. It's a minus f of x. Now this a times f of x, it controls how far up or down the graph goes. So that's its amplitude, how far up or down, and a modulates the amplitude. Now, let me ask you, have you ever heard of the phrase amplitude modulation? You actually have probably heard it quite a few times. Does that sound familiar at all? Amplitude modulation.
Like AM, FM radio?
That is correct. That is precisely what AM means, amplitude modulation. The idea with AM radio is that the radio tower puts out this wave whose amplitude rises and falls and rises again. And the rise and fall and rise of the amplitude is the sound, is the music sound that is, or voice sound that the radio is transmitting. The idea being that the radio waves oscillate a lot faster than the sound waves do. Now, let's do this inside, f of bx. Now here, multiplying by a constant outside makes amplitude, modulates how far up or down this goes. Here, multiplying by bx inside affects the graph, how squeezed or stretched it is horizontally. If b is bigger than 1, then f goes through its range faster. And that means there's a horizontal squeeze. If b is between 0 and 1, f goes through its range more slowly, and so that corresponds to a horizontal stretch. And if b is less than 0, then it flips left for right. So for example, if here is graph of f of 2 of x, and f of 2x runs through it more quickly, squeezed horizontally. F of a half x is stretched out horizontally. F of negative x flips this left for right. So f of bx, it modulates frequency, and yes, that's like frequency modulation in radio, where the radio tower sends out a signal at a constant amplitude, but it's frequently squeezes and stretches and squeezes, and those changes represent the sound that the radio wave is transmitting. Now, one difference between AM radio and FM radio. So with AM, when the signal is briefly at a low point, it's vulnerable to interference from natural sources, lightning or people's turning on cars or what have you. This is so it becomes vulnerable to electromagnetic static. And so AM radio tends to be a little lower quality. That's why it's only used for voice transmissions, not for music. FM, the amplitude is always a constant, so it's less affected by random electromagnetic static. And that's why you have all the music channels around that. Now, if this were a graph of y equals f of x, then y equals minus f of x flips up for down. It's up, down, flip. Here's y equals f of negative x. That flips left, right. So this graph looks like this, flip left for right. And if you do both of them, y equals minus f of minus x, that flips left for right and up for down. And when you do that, you get a 180-degree turn. Take something, flip left for right, and up for down. That is a 180-degree turn, like this. Let's do some examples. Graph y equals the square of x minus 3. Well, y equals x squared is this U-shaped graph. This minus 3 moves it, means we have to move it to the right 3. So it's a U-shaped graph with bottoming out at 3. Graph 1 over x plus 4. 1 over x is this hyperbola. This plus 4 moves it up 4, so it looks like this. So instead of having a horizontal asymptote for y equals 0, it's asymptotic to y equals 4. Here is, now this will do several things in a row. Minus x minus 2 cubed. So what we do is we take an x cubed graph, then we, okay, here we have an x cubed graph. Then we have a minus x cubed graph that flips up for down. And this x minus 2 shifts it right 2. So it looks like this. Here this has a what's called an inflection point at 0 by 0. Same as 0 by 0. Here the inflection point is at 2 by 0. Going up, pausing, and then going down. Going down, pausing, and going down. All right, here we have a graph. F of x goes to negative 5 by 0, negative 2 by 3, 2 by negative 3, and 5 by 0. Graph f of negative x plus 3, part B, at graph y equals negative twice f of x plus 3. Okay, for part A, you start with this graph, flip it left for right, that's f of negative x. Then add 3, you raise it by 3, so this is the graph. So we take this, flip left for right, raise it up, and oh my God. This is wrong. It should be this raised. This is incorrect. I have this backwards. I'm going to have to change that on the form. This is 1-6, page 7, part A. All right. Here we have, we're going to take this minus 2f of x. So it turns this upside down and stretches it by 2 like that. Then add 3, you just raise it by 3. All right, I'm going to have to fix this. This is a mistake. All right, we proceed.